I couldn't handle the green anymore. We're back to something not so green. So here's a problem we're going to look at. And notice that the instructions mention nothing about Green's theorem, and that's going to be up to you to figure out whether or not you need to use it, and if so, how to do so. So let's take a moment and maybe sketch our curve C. It's nice to get a glimpse at these things. So we're just going to go out here to 1, 1, and then negative 1, 1, and then here, and then there. And we just have this square. Looks like that. And then we'll have positive orientation, so we're going around the square like this. And so before we do anything, I'm going to check and see, is the associated vector field here conservative? And you might be asking, what vector field? Well, remember, I know that I can view this integral that's in front of me as the integral of a vector field. Let's scroll up again. We put it in the comments right here, where P is the thing you're integrating with respect to dx, and Q is the thing you're integrating with respect to dy. So the point is that I can write this integral. This is just the line integral along C of f dot dr with my vector field f equal to x squared y comma x y to the fifth. That's my PQ. And so I'm going to rewrite that, x y to the fifth. And so now I want to check, is this thing conservative or not? So let's just check real quick. I'm going to compute p partial y, and I get 5x y to the fourth. And you can already see if I compute q partial x, I get a 2xy. These are not the same. So I'll just say these are not equal. So we know f is not conservative. I'm going to need to add some more space. So close your eyes real quick while I look at the next problem and slide it down. Don't want you to see ahead too much here. I think we can put it right there. There we go. All right, anyway, so this thing is not conservative. So unfortunately, I can't just snap that the answer is 0. But it's worth checking that. That's good to know. And I'll actually make use of the fact that I've got p partial y and q partial x. I've already computed those if I do use Green's theorem. So I want us to think about what would happen if we actually tried to do this directly. So if we tried to do this directly, I would have to parameterize each piece of my curve C. So I'd have to call this side C1, and this side C2, and this side C3, and this side C4. And let me just show you how you'd parameterize C1. For C1, you'd realize, well, x is just always 1. So x is 1, and we could say y is t, and t is going from negative 1 to 1. And so your parameterization for C1 would be, what, 1t, t between minus 1 and 1. And you'd have to do that for each one of these curves. It would actually take 4 different line integrals to be able to compute this. So let's just say the direct approach would be 4 line integrals. We don't want to do that, so let's say, yuck, that doesn't sound very nice. Let's try Green's theorem at this point. We can apply Green's theorem. To apply Green's theorem, we need the components of our vector field to be decent. They need to have continuous partials on the inside here. Well, these are polynomials, so they're well behaved. And we're good to go. Let's do it. So we can say, okay, by Green's theorem, and I like to take the original integral that I have, at least a version of it, so that's this one. And I'm going to say this, by Green's theorem, this line integral is equal to the double integral over d. I'll fill in the bounds in a minute. It's equal to the double integral over d. And now what do we say before? Think about what you have to plug in there. You have to plug in q partial x minus p partial y. And so we'll just put a dA. So now at this point, I've switched entirely to double integral mode. I'm looking at my picture up here, and I'm asking myself, do I want to cut this type 1 vertically or type 2 horizontally? And you should be saying it doesn't matter. Everything is constant. This is going to be a great double integral. I like it a lot. It doesn't get any better than double integrals over rectangles. That's about as good as it gets. We should go back to our Christmas colors because this really is a wonderful thing. So we're going to have double integral. Let's write down the integrand first. So we had q partial x was what, 2xy. And then we're subtracting p partial y, which was 5x y to the fourth. And then I don't care how you want to set it up. You're welcome to choose. I'll set it up dy dx. So we'll go type 1 just because we can. And y goes from -1 to 1, and x goes from -1 to 1. It's just great. And so I won't work this out. This one is just pretty straightforward. Why don't you pause the video and work it out yourself, and you should come up with -4/3. And if you have a little time, I know a lot of you are crazy busy. If you're enjoying this and you have a little time, then I'd love for you to pause the video and try and work out the 4 line integrals and see that they do sum to -4/3. Now, let's try and keep in our minds the meaning of these line integrals when we can. There isn't always clear meaning for the problems that we're working, but keep in mind the skills that we're learning are useful for computing lots of things. So everything we're doing has ways of being useful. This problem, though, there is a physical meaning. Keep in mind that when you do a line integral of a vector field along a curve, then you are actually getting the work done by the vector field and moving a particle along that curve. And so the point is as we move a particle around this curve C, that the vector field is actually doing more against it than for it. It's actually giving you a total work of -4/3. So let's stop this video here, and in the next one we'll keep going.